All right, hello, welcome to the Off by One security stream, our first one of 2025. Thankfully, we've got the great Jonathan Reiter as our guest today. He's been on before. He's also one of our mods on the Off by One security Discord channel, so I'm sure you've seen him over there. I don't know if he wants people to know his handle, though, and associate that attribution, right, John?
Yep. Well, shadows.
Yeah, it's Shadows. Yeah, of course. So, cool. Welcome, everyone. See folks joining in now. I never know when to get started because it's always that latency between you start the stream and then people start joining in. It's interesting that we get most of our viewers from X, from Twitter. Like the one stream we had with Alyssa Assange, we had I think over 6,000 live Twitter viewers and only maybe like 800 from YouTube. So I always think that's interesting. I never thought of X being a platform that was going to be really good for streaming, but I guess I was wrong. But we also stream out to LinkedIn as well. We haven't started Twitch yet. I don't know if we should go in that direction, but always in consideration if you think it's good or not. But welcome, everyone. Screen is black for you. Shouldn't be. I think it's working okay for everyone. But let's just jump right in. So our topic for today is taking a look at C and also debugging C with WinDbg or WinDbg or WinDbg or whatever you want to call it, many different ways. I'll tell the one story just because it was funny. I was in London teaching a class, and it was a co-teach with another instructor, and we had students from all over Europe attending, and this one particular student from Italy corrected me in my pronunciation of WinDbg or WinDbg, and he said, no, it's WinDbg. So that's kind of where the WinDbg thing came from. I think that's pretty a funny way to say it, and I've never forgotten it since. So, but to be fair, Jonathan named the title for this one. So I guess, Jonathan, you want to give, for folks who don't know you, I know you've been on before, appreciate it. Give a little background about yourself, just so folks know who you are.
Yeah, sure. Yeah, thanks for having me on yet again on the channel. So for those that don't know me, my name is Jonathan Reiter. As Steve said, I teach for SANS, or wrote a course for SANS called Security 670 to focus on writing implants for Windows, and got a couple classes for that coming up. So if you're interested in that sort of thing, feel free to message me on Discord or whatever. Be more than happy to talk to you about that. And right now, my full-time gig is a developer for Windows. Gee, go figure. Spend a lot of time in user space, a lot of time in kernel space as well. And my primary language is C++, even though today what I'm going to show you all is with C. Figured this would target more of a entry-level kind of audience, and we'll stick to that a little bit. And also with WinDbg, be entry-level debugging stuff.
Yeah, but certainly, as always, if you have questions, we definitely encourage you to ask them. Especially, if you do have more advanced questions, Jonathan, then I can certainly answer those for you as well. But like you said, we're going to stick to kind of, it's one of those things where, yeah, off by one barbecue. I don't know. We're talking about like the idea of maybe doing a conference or something, or a gathering or meetup. We're actually getting merch put together. Miscreants, the team that puts together, does graphic design and such. They're designing some cool merchandise for us. So hopefully we'll be able to get that out pretty soon. I was hoping to have it done by the end of the year, but that all ties in. But yeah, when we teach classes a lot of times on exploit development, when we know that the audience is mostly going to be beginners or people who are obviously aren't advanced, we often use debuggers like X64 debug or even Immunity debugger or other ones because they're a little bit more intuitive. They're more graphical, aesthetically pleasing, and again, intuitive for people who maybe don't have much experience with command line debuggers. If you've lived in the world of GDB on Linux, of course, then you probably dealt with mostly the command line side, unless you're using some of the graphic front ends like DDD or EDB. But either way, WinDbg is truly the only supported Ring 0 debugger from Microsoft. And obviously, a lot of times we're debugging Ring 3 applications, and we don't need to look into the kernel. But if you want to go into the kernel, you need a Ring 0 debugger. And there were old ones in the past, Soft Ice and others. And I know there's a couple out there right now that actually do support some Ring 0 debugging. Also, of course, we've had folks on and talked about things like JTAG debugging, more on the hardware side to get into things like the secure kernel and hypervisor debugging. But WinDbg is extremely powerful. And as a developer, if you have a development background, a lot of that power comes from your ability to literally code in the debugger to get some really cool information out of it and kind of take things down to a more specific view, especially when dealing things like heap-based memory and trying to find things out there with all the mitigations and randomization and all that going on and all the changes to the heaps over the years. You know, in the old days, we had the look-aside list, and then it came out with the low fragmentation heap and the segment heap, and it just gets more and more complex. So when you need that power, WinDbg is a really great tool for it. So I think this will be a great one to kind of take a look at approaching debugging C or Windows-based applications with WinDbg. And of course, I'll be bugging Jonathan to come back on and do a more advanced one later on in the coming months. But yeah, if you do have the opportunity to take his course, the 670 course, it's fantastic, especially now in the age of you can't just take Meterpreter or Cobalt Strike, things like that out of the box for your implants or C2. You need to customize things, your loaders, stagers, whatever, because the stuff's going to get picked up by EDR. So being able to customize things, test different EDR products to see which ones you're able to get around, really teaches you kind of all of that. And it's a really, really great course. So if you get the opportunity, I definitely recommend doing so. But without further ado, I guess, Jonathan, you want to go ahead and just kind of get started with letting us know what you're going to be talking about today.
Yeah, sure. Thanks for the plug again for the course. Yeah, so what I want to talk about today, and some of you may already be familiar with it. That's totally fine. That's cool. And if you are, it'd be sweet to chime in with your experience about this. So I want to focus on obviously C programming for Windows. And this is going to be basically specific around compiler intrinsics. And a lot of people are kind of, say, new-ish to compiler intrinsics. Some probably have never heard of it before. So that's the audience that this is going to be really geared towards. And so instead of me just going through the motions of coding live in front of you, which I think might be a little bit boring, I already have an example already set up with a ton of comments that you can look at. But I'm going to explain the source code in detail. We'll compile it as a debug build with symbols, and we'll transfer that over into WinDbg. And I'll walk you through the motions of how to get oriented with the debugger, its interface, all that type of stuff, some commands that are helpful for not only just debugging, but specifically for taking a look at some of the registers that these intrinsic functions are going to be utilizing pretty heavily. All right, so that's what we're going to get into today.
Are you going to be able to share the code for folks afterward?
Yeah, I don't mind doing that. That'd be good.
Yeah, cool. I think folks will probably like, especially watching later on, and want to follow along.
Yeah.
One last thing I'll say before Jonathan gets started here is, you know, I've said this many times before, where a lot of people who come from the attack space, pen testers, red teamers, whatever, who want to go into exploit development, don't have a coding background, that end up spending more time in disassemblers and really focusing on that side of the house as opposed to decompiling things. And when you're working together with a debugger and also a decompiler at the same time, you're going to be a lot faster. So really picking up those programming skills and fundamentals and really taking that dive in to get proficient in C, C++ is going to really help you out in the long run versus just being stuck in the world of assembly all the time.
Yep. Cool. Awesome. All right, cool. Got the screen share up, rock and roll. Okay, awesome. Yeah, just to echo and add on to what Steve was just saying, and I know, so sad, Windows side. I feel you though, but the opposite. Whenever there's a Linux guest on the stream, I'm like, Linux. So yeah, I feel you. But yeah, so getting into realm of customizing your tooling, no longer being able to utilize things just out of the box. Even some of the commercial C2 frameworks these days, you have to be able to customize it, add on to it in some way, shape, or form. And so knowing how to do that is very, very beneficial, whether it's C, C++, or some of the other languages that you might want to use. So compiler intrinsics. What in the world are they? You can look at MSDN. I have the documentation up in front of you. And if I can get maybe Steve or Randall to share the link with everybody, I'll paste that in so y'all can take a look at the resource and go directly there. There's plenty of reading material on the MSDN pages about intrinsics, what architectures they're applicable to, and specifically what functions are available or not available for certain architectures. Okay, so it's not like you're gonna be able to do some of this stuff with 64-bit and have it work across ARM or have it work across even 32-bit. So you have to be very specific for the architecture that you're going to compile down to. And as you can see on the left-hand side over here, we do have specifics for ARM, ARM64, x86, and AMD64 intrinsics. Okay, and what's really cool about these, I'll scroll down just a little bit, but there's no way on earth I'm going to read all this to you. But basically, what I like to use compiler intrinsics specifically for implant dev and also for shellcode creation is when you call these functions, they're not actually a call instruction that generates a typical function call. There's no function prologue that has to be set up. They're actually forced in line, and they're known internally to the compiler itself, and also the architecture, like the CPU itself. And so they're highly optimized in that sense. And so what's great about that is specifically for shellcode creation is the opcodes or the instructions that these functions generate are automatically position independent. So some of the examples, or one of the main example I'm going to show you here in just a little bit, if you were to compile it down, you'd be able to extract the opcodes from the text section and treat that as shellcode and inject that into a different process if you want to go across process address boundaries or whatever, or keep it locally within your own process. It's very situational dependent based on what kind of target you're on. But you can do a lot with compiler intrinsics. And there is a complete list also on the MSDN documentation. So you can check out some of these different links here. We're going to be specifying on 64-bit for this stream. I think that's probably the most common architecture out there for Windows installations. So you can go through this and you can kind of look at some of the intrinsic functions that are there. Now, some of you probably, if you've done any kind of Windows dev already, you may have used a couple of intrinsic functions already. One of them is probably the read GS keyword or the read FS double word. Let me see if I can find that here.
And so someone's asking if there's any relationship between constructors and destructors and compiler intrinsics.
Not for this.
Yep.
Not for this. Yeah. So this one right here, the read GS keyword here. You've probably used this before if you are a current malware dev and you're trying to read and gain access to the process environment block. Okay, basically, this will return to you the pointer to the process environment block as long as you know the offset for this. Okay, so I'm not going to dive deep. That's a sideline conversation into what the PEB is, walking the PEB, finding linked modules and stuff like that. But that could be a fun stream in the future of how to do that and how to compile that down on shellcode with the help of some of these intrinsics. All right, so that's MSDN is also this great resource, all right? But in addition to that, you have the Intel documentation, and it has a nice little search feature for all of the intrinsic functions that you can use. Okay, you can do all kinds of crazy things like comparing. Okay, you can go ahead and check on that box and find all the intrinsic functions that will do comparisons. So if you want to do string comparisons, you can do that highly optimized with intrinsic functions. If you want to do any kind of bit shifting and stuff like that, there is a category for shifting. Okay, and then somewhere, where'd it go? Cryptography. All right, if you want to do any kind of crypto, AES type stuff, I was working on a small example for using nothing but compiler intrinsics for AES encryption. That way, if you have an implant that needs to do some kind of communications with the C2 infrastructure, you want to make sure that your payloads and your traffic and all that stuff are secure and encrypted. And you can do that with compiler intrinsics. It makes it really nice. It's just a lot more, to be honest, it's a lot more difficult using encryption with nothing but these intrinsic functions. But the Windows APIs, Win32 APIs, are a lot easier to use for encryption. All right, cool. So let's go ahead and jump over to the C side here. Come on. All right. So I mentioned before, I don't want to just code live. Right? I have separate workshops for that. I did a whole 10-part series of an introduction to C where we coded live together. So if you're not familiar with those, that workshop series, that is the introduction to C for Windows. So the 10 parts is like 20 hours worth. So what I'm going to do is I'm going to walk you through this source code here. And I'm inside of Visual Studio 2022, the Community Edition. And I'll walk you through all this stuff, what I'm doing with everything here. And then when we compile it, we'll run it a couple times. We'll try to validate everything. And we'll use an external application as well to validate some of the stuff. And then we'll dive into WinDbg for a little orientation into that debugger and how you can specifically look for the intrinsic functions that we used for this one here. Okay, so the first couple of lines here, 1 through 5, what I have going on there is basically all of the header files that you have to include for using intrinsic functions. I try to add little comments for what headers bring what data types and what functions. So you can see there's a couple here for this specific data type here, this M128, and then we have ones for AES as well, just showing you some other examples. Okay, if you check the Intel documentation, that huge link here, these ones should show you the header files required, where these are implemented. I think MSDN documentation should show you that as well. All right, so the next thing I have is this intrinsic XOR function that's just a prototype to say, hey, you know what? I want to go ahead and send you some data that I would like to run through some kind of XOR routine. A lot of times it's very useful to like hash strings. You can create a custom XOR routine to create like a hash or 4-byte hash of strings. One of the nice things about doing that is you can eliminate some of the strings inside of your compiled binary. That way, when a malware analyst or whoever is looking at your binary, the strings utility isn't going to be hitting anything that might be sensitive for your program. So all those sensitive strings like API names, names of DLLs, or any other strings, you can, in a sense, hide them a little bit with like a hashing utility. So I'll show you later an example of that. And then down here, we have the main function. Okay, this is going to be the main link or the main entry point for our program. And yes, I can share this link here for the Intel. Let me send that out. All right. Steve or Ryan, if you could share that one.
Yep.
Cool. Thanks. Okay, so inside the main entry point here, not trying to do anything fancy with this, not trying to create our own custom entry point, not trying to free ourselves with a CRT or anything like that. I have a whole 2-hour workshop on how to do exactly that. So check that out if you would like. What I have here on line 18 is just a straight up string, a test string. Quite literally says this is a test string. And I want to go ahead and grab the length of that string. All right, that's going to be useful because we're going to pass that to our little helper function to basically XOR this string with a key. Over here on 21, I'm calling a function to dynamically allocate some memory from the default process heap. All right, so heap alloc has a void return type, meaning I have to cast that, do a type cast to the data type that I want to deal with. So heap alloc will go ahead and allocate that chunk out there in the heap world, and the size of the heap chunk that I need is going to be based on the size of my string. Okay. And then I wanted to make sure that when we allocate this, let's go ahead and zero everything out just to be safe. And then we'll go ahead and store that in a local variable, just called XOR data. And we have to do an error check. Okay, you have to make sure that heap alloc actually succeeded. And if it didn't, and we didn't make this check, then you could be playing around with a null pointer, and there's all kinds of nasty things that could happen if playing around with a null pointer, like dereferencing null pointers is definitely not a good thing to do. So we go ahead and make sure we do a little sanity check to make sure we actually have a pointer to our chunk of memory. Okay, with that in hand, we can go ahead and pass off those arguments to our helper routine. I just call it a wrapper around some intrinsics. Okay, so this is my intrinsic XOR wrapper, passing in the plain text string, the chunk that we just allocated, and basically the size of that chunk. So here's where it gets good. Right here, skipping 61, 62, it's just initialization of some more local variables for this function. And at 65 here, this is going to be the key that we're going to use for the XOR routine. And I went ahead and made sure that this is a 16-byte key because with intrinsic functions, they work very well with aligned arrays and aligned memory. And then you can deal with 16-byte chunks at a time for efficiency. And what's great about them is they will go ahead and generate single instruction to go ahead and carry out some complex actions. So we'll see here when we get to some of these functions, we'll look these up inside the Intel docs, and it will show you what the instruction is going to be. Okay, so this key is just a random key. Okay, it doesn't make it's pointless. It has no meaning. Just a bunch of random bytes to go ahead and satisfy the requirement of using a key for our XOR routine. All right, and we could go ahead and start a debate out there for everybody listening. Is XOR a cryptographic function? Technically, is it called? Is it classified as crypto, or is it something else? Right, it does involve a key. Okay, so have fun with that little debate if you want to get into that. So the next piece that we have to do here is we are still not dealing with some of these specific registers that deal with these SSE2 instructions. Okay, so the beauty of these registers, like these XMM registers, is being able to handle 4-byte chunks, 8-byte chunks, 16-byte chunks, all in one fell swoop. And it's very nice to be able to do that. So we have to go ahead and tell the CPU that we want to go ahead and load our data into an XMM register to go ahead and get things ready for processing all of that data. Now, there's a very specific data type that we have to use with some of these intrinsic functions. And you can see that data type here as M128I. And we're doing a little typecast there for pointer, okay? M128I splat. Okay, and we go ahead and pass it our key. So we go ahead and say load, all right? Load, load U, SI128. So go ahead and call that intrinsic function and get everything loaded into the XMM register. Now we can go ahead and say, this is my loaded key. It's in the register. We can go ahead and now start to take action using this key. Okay, so then what we'll do is we have a for loop that's basically going to jump over our plain text data 16 bytes at a time, or 16-byte chunks. Multiple ways to do this. This is not the only for loop version that you can do. This is just one of many. One of the things I love most about C and C++ is the fact that there are many ways to do the same thing and have the same effect. So it's really nice there. All right, so we'll go ahead and start implementing our for loop there. And the first thing we have to do is actually grab some of the plain text data. Now, because we're wanting to operate on 16-byte chunks, we'll go ahead and say, let's go ahead and load up the first 16-byte chunk. So at index 0, okay, so at the very first iteration of this for loop, our index value is 0. So we do some indexing into the plain text array, if you will. And we'll say, just grab me the first 16 bytes that you see. And we'll go ahead and load that up into the register. And then we're storing that as this local variable here called chunk. Okay, this is going to change every iteration of the loop. Okay, so once we have that, we can go ahead and actually XOR the first 16-byte chunk of the plain text with our 16-byte key. We call the XOR SI128 intrinsic function, and we say the current chunk against the loaded key. Okay, again, emphasis on the loaded key. You cannot pass the regular key up here because it has not been loaded into an XMM register. Okay, all right. Once we have that, we have our current chunk completely XORed, ready to go. And then we can go ahead and store. We can store that result. Excuse me, we can go ahead and store that off. All right, with here, XOR data at this index where we are right now inside the for loop. And then we go ahead and process the next 16-byte chunk. We keep on going based on the length that we got earlier. But that's not it. We can't just stop there because not everything that we're going to be dealing with is going to be a perfect alignment of 16-byte chunks. We're going to have some straggler bytes, some leftovers, if you will. So we have to make sure that we handle that. And this is for the leftovers. All right, the for loop on my line 90 handles the leftovers, and you can do any kind of XORing that you would like. This is the way that I just chose to do it. And sadly, you cannot use an intrinsic function for the leftovers because those are for dealing with chunks of data at a time. Okay, so that's a little walkthrough of the source code. Now I want to show you some of the documentation on the Intel link here. If you go to the search, just paste in one of these. A lot of times you might have 2 hits, which is fine. You can click on any one of them, and maybe you check out both of them just to try and see what subtle, and I mean very subtle differences there are between these 2 intrinsic functions. So the synopsis here for this one, it tells you what header file you have to include. Let me kind of zoom in here. Enhance. So it tells you the header file that you have to include. Cool, we already have that. We're good to go. And it tells you what the instruction is going to be for this intrinsic function. So move DQU and then XMM and then the M128. Okay, so the emphasis on the M128 data type. And you can see the CPU ID flags, SSE2. And then it's nice because they give you a description on a very, 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 very low level operation, which I'm definitely not going to get into for an entry level stream for C and debugging. Okay, so basically the description is we're loading 128 bits of integer data from memory into destination, right? The mem address does not need to be aligned on any particular boundary. Okay, that's specifically what's happening here. The data here is not aligned on any boundary whatsoever. It's not 16-byte aligned or anything like that, although we could do that. And we could do that, and we could go ahead and use a different function like this one. Okay, if you want to try to use this version, you can. The description tells you that specifically coming from unaligned memory. Okay, and it gives you a little bit more to say, hey, this might perform better than the load U when the data crosses a cache line boundary. All right, so that's how you go through and look at the some of the help, some of the descriptions, and some of the documentation, even though it's still kind of lacking, in my opinion, documentation-wise, for some of these intrinsic functions. And let me show you the XOR one. All right, we only got one hit, okay? So we don't have to worry about playing around with different versions and trying to understand those subtle differences between versions. This one, same header file, so cool. We already have that included, great. And the instruction here is supposed to be a PXOR with an XMM register against an XMM register, okay? And then of course, SSE2. And we're gonna compute the bitwise XOR of 128 bits. Okay, and then we'll store the result in the destination. Okay, cool. That's exactly what we're trying to do, right? That's our whole purpose for this particular one. Okay, then we'll go ahead and store it off, and away we go. And once we have that, once that helper function returns, just have some printf statements to show you like a little before and after, if you will. And then we'll go ahead and dump out the XORed data in hex. And we just do some cleanup. We free that chunk from the heap. And then I just go one extra step more and nullify that pointer that was previously pointing to that chunk of memory. I just null that out. So let me go ahead and build it. Oh, wait, not cool. Build one succeeded. And we can go ahead and optionally just go ahead and run this inside the Visual Studio debugger. And let it roll. Okay, cool. I know the font is a little bit small, but basically we're just saying this is a test string. So just print that out, the plain text, and then the XOR data, just all those hex bytes. Okay, we got starting with a 4B and ending with 4E. So what we could do to validate that our code kind of works a little bit is to go over to like an outside resource like CyberChef and try to replicate our little XOR routine, if you will, using the same key. Okay, so that's what I have here inside CyberChef. I loaded our 16-byte key that I was using inside code on the C side. And then whatever that result is, just go ahead and basically pipe that off to this recipe here to hex, right? I don't want the output down here to be trying to render all those bytes as ASCII or whatever. Just show me the hex. That way I can match it up with the output here. Okay, so I'm just going to go ahead and grab the test string. Let's copy that and paste it over. All right, so we got the bytes of 4B, blah, 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 and then 4E. Okay, and I think we're good. Where'd it go? Yeah, all right, cool. So we have a match, all right? So we have external validation that everything that we're trying to do works, all right? We have a match from a third-party resource of our XOR operation, so sweet, okay? We're good to go. Let me get caught up on some of the comments, questions here real quick.
Yeah, I would say, yeah, the couple questions like with intrinsic functions, is the purpose for performance is one question.
Yes, absolutely. Intrinsic functions are amazing for performance. The opcodes that they emit are highly optimized for the architecture that you've chosen for like 64-bit, for example, AMD 64, highly optimized. The reason behind that is because, and I'll show you here in just a second when we look at the disassembly, there is no actual function call. Okay? That way, like for example, intrinsic XOR. This will generate a full-blown call instruction, aside from talking about various optimizations and stuff like that. This can generate an actual call to the function. We'll set up the function prologue, and it has its own stack frame and all that jazz. All the variables we passed in, registers like RCX, RDX, R8 for the first three here, all that type of stuff, right? So with intrinsic functions, that doesn't happen. You won't see a call for this. it's just going to be a single instruction, right? A single instruction, which is very, very nice for that optimization that you were just talking about. Hopefully
Here's
I
another
answered
one
the
on the
question.
screen. There's
X or X separately from AES.
no. Is there a way to have this
No.
documentation queryable in a terminal for?
Oh, you know, I don't know.
Wonder if Shell GPT could help you out.
I don't know. Yeah, maybe. I'm not sure. Yeah. No, that's a good question though. I'm
No,
not
the
really
rest of the
sure.
questions so far unrelated to what you're doing.
Okay. Okay. Probably the XOR crypto kind of
Yeah, it's
debate.
just yapping about
Yeah,
crypto.
yeah, yeah. Okay. All right, cool. All right. All right, so cool. So we got the compile binary. We ran it, success. We validated with CyberChef. So let's go ahead and flip over to WinDbg and see what we got there. All right, so I'm not using classic. I'm using full-blown modern WinDbg. It's no longer called preview, thank goodness. So anyway, this is WinDbg. All right, if you've never seen it before, welcome. And the UI is pretty slick. It's nice. It has a lot of cool features and stuff like that. And so a little bit of orientation here is you can set up these windows however you see fit. And for the most part, it will go ahead and save this workspace on its own, and it'll bring you right back to where you left off. All right. So this is kind of how I like to have everything. Command window over here, disassembly, and then some registers. Sometimes I'll swap out registers with like a memory window if I need to explore like just raw pages of memory and stuff like that. Okay. All right. So this is what I like. All right. It's my own custom little setup, nothing too fancy. But you know, it works for me. And one of the things that you can do with WinDbg is you can come into the file and look at some of these options over here. So you have like launch and executable. Okay, cool. That's self-explanatory. Launch executable, but the advanced version. It's almost like you need to put that in air quotes. That one is kind of cool because it supports something called TTD. So time travel debugging. You could probably have an entire stream dedicated to time travel debugging and all the features for that. It's really cool. High level overview of TTD is the fact that you can basically record and trace the execution of a binary and play that back as many times as you want, and you're going to have the exact same execution and code flow. So if you're interested in doing like exploit dev, vulnerability analysis, or whatever, you're taking a look at some crazy vulnerable program that you've seen before, you'll never miss that ripe opportunity for the exploit. So TTD is pretty cool. We can attach the process, and you can open up a dump file. But the dump file, what's kind of cool about that is it doesn't have to be an actual dump file. You can open up executables like DLLs, kernel drivers like sys files, and executable images. So I can show you that real quick. All right. So when you open up an executable image, like the intrinsic XOR binary that we just compiled down, this is not it in a running state. This is WinDbg. Go ahead and looking at this thing straight from disk, as if it is kind of like a dump file of sorts. Okay, so everything is here on disk. So some commands that you might be familiar with, for those that already are familiar with WinDbg, are not going to be there. Okay, one of the things that you can do is you can explore the actual image itself. You can dump headers and stuff like that. So you could use the bang DH for like dump headers. And what I like to do is I like to copy and paste a lot. So 2 right clicks, gets it down there. Then we'll go ahead and just dump all those headers. Okay, so that's kind of nice if you want to take a look at some basic PE parsing brought to you by WinDbg. And on the far left-hand side at the disassembly, it kind of shows you already where the entry point is for the program. It says main CRT startup. Okay, so intrinsic XOR, the name of the module, the bang, which is basically a separator, a delimiter, and then we have the function name or the symbol name, like main CRT startup. Okay, this binary was linked with the C runtime, and so it is going to basically kick off the entry point for our program, which is main. Okay, so you can click on main in the disassembly window. You can also look at it inside of the command window. So I can kind of show you how to do that. There's a command called X, straight up X. Has nothing to do with Twitter or what's now known as X. This was here first, but you have the X, excuse me. You have the X command that helps to look at like symbols and data and stuff like that, brought to you by some modules. So what we can do is take a module and kind of do like a wildcard search, if you will. And we have all of these symbols or functions that are present inside this binary. And it looks like a mess, and it's kind of, it is a mess, but you can see all the things that are internally present. And a lot of this stuff is just there because we linked against the C runtime. So a lot of this you can just gloss over. And for right now, it's completely irrelevant for what I'm trying to showcase. Okay, so if you have something of interest that you want to look for, like we know main, right? We know main is a function here because we made it. You can do a wildcard search for any other function that might have that text inside of it, like main. So we have the X command, intrinsic XOR, the bang. I'll leave the splat there, and I'll just say main, and we'll do another splat. Okay, so did a little search and said, hey, here are all of the other things that have main inside of it. Okay, so it's really nice, really comes in hand if you don't know the full name or whatever for a symbol that you're looking for inside of a binary.
Yeah, don't want to get too backed up on related questions that are popping up here. So you want me to ask you a couple?
Yeah, go for it.
One is, I assume you're going to show the difference between regular XOR and using the intrinsic. Typically, AVs will flag anything like a simple XOR, which is XORing something from .data segment by looking for the loop, such as XOR RDI against something.
Yep. You will see that. Yeah, you'll see that difference because the stragglers right here that weren't handled or didn't fit evenly as a 16-byte chunk. We'll go ahead and take a look at that. And this is that traditional XOR routine. There are some cool blog posts out there. Kind of caught me off guard. I didn't have those handy, but there are other ways in C, obviously, to do the exact same thing as the XOR operation without doing the little XOR bitwise operator. Okay, so multiple ways to go ahead and avoid that kind of signature of, hey, we're doing an XOR routine. But this will showcase that little compare and contrast that you're looking for from this to probably what everybody who's done XORing a C has seen before. Is that a question there?
Yeah, and the second part of that question was, or comment was, can you comment where to store the shellcode so that antivirus doesn't immediately flag it?
So many places, I suppose. What's the best place? I don't know. It depends on what EDR you're going up against. Everything is so, dependent on who you're fighting. But you can store it obviously within the text section itself. You can store it in as a resource. As long as you're able to find it, that's the big piece. I've stored full-blown DLLs as a resource and binaries and do get execution that way and bypass some EDRs with stuff like that. So there's real really no, let's say, silver bullet or golden bullet. They'll go ahead and say, store it here, and you'll bypass all the EDRs. I think it's very dependent. But one of the things that you can do is just make sure that your shell code is encrypted or obfuscated in some way, shape, or form. That way, if you're dropping something to disk, any kind of scanning engine or whatever, something gets kicked off on demand, shouldn't be able to see that. And then that's a whole can of worms because you got to deal with entropy and stuff like that. Yeah, so multiple places that you can store it.
Yeah, we'll do a session coming up at some point. I'll do one on shellcode smuggling techniques with like JIT compilers and such. Just some interesting things there. Another question was on Discord. It was I don't want to go back and look at it. I think it was, what's the difference between a lambda function and an intrinsic function?
So lambdas, are you referring to like a C++ lambda?
I just assume like
examples.
Python inline function or something. I don't know.
Oh, God. If you're thinking like a Python one-liner, obviously the differences are quite huge. Lambdas, that would be interesting because there's a really cool resource out there called C++ Insights, cppinsights.io. So what you could do is you could go ahead and create your lambda inside here and take a look at the internal insights for that C++ source code. And I use this all the time to kind of see what's happening behind the scenes by the compiler or what might happen. So you could check that out yourself if you're curious about that. It's a really solid resource. But off the top of my head, I'm not really sure about some of those key differences there.
Cool. Last one for now, then I'll let you continue here. Is there a way to filter out the C runtime functions with what you were just showing?
Kind of like a negation, if you will, in the search.
I believe so.
Yeah. I'm not sure if there's a negation that's built into like that X to say, hey, show me everything that does not have this inside of it, like anything that's SRT related. What I kind of do is I like to filter down, right? So start with a wide search, and once I kind of see some of the hits coming in, then I'm like, oh, okay, now I know more about the function I'm looking for. So let me go ahead and refine like my wildcard search so it's not too crazy, not too widespread.
Cool.
Yeah, good question. I think we're caught up ish.
Yeah, we're caught up for now. We're good.
Yeah. The good old classic .text. Yeah, it's an option. Is it the best? No. Okay. All right. So looking at the disassembly here, we see on the disassembly side of the main, all right, the main function, and then inside the command window, we found right here the main function. So one of the things that you can do is use the command U to go ahead and unassemble or disassemble an address or a function name. Always helps because we have symbols, right? We compiled it that way on purpose just to make this show and tell a little bit easier for everybody. Typically, this isn't always the case. All right, so we just saw a basic default number of lines that is presented to us. If you want to see the whole thing, you can just do UF, right? So disassemble the entire function, and we see everything else. And what's kind of cool about this is as you go through the motions, which I kind of recommend everybody do this as you're getting started, understanding C and how it looks after it's been compiled, is make sure you have those symbols, because when you're going through all of this, you can see where inside of my source code are these instructions kind of relevant, or where are they tied to. So we see inside of main.c at line 42 basically is where these instructions are coming from. So you can go through and be, all right, what the heck was that 42? I don't remember. So you can go through and look at the source code file find 42 and be like, okay, so we're right around there, right around printf. Okay, so it's kind of nice to get your orientation set when you're in at the disassembly level. Okay, then once you get really good at that, get away from the symbols, all that stuff, and you can like strip symbols or compile it down without what's called a PDB file. All right, so make sure you don't have that. And that way it can really help you start to step up your skills using a debugger. All right, so give me a second here. Forgot to plug in my charger.
I was just commenting that UF stands for unassemble function because, disassemble's too obvious. So we got to make it weird because we're Microsoft.
Yes. Microsoft and their naming conventions, sometimes they're amazing and sometimes just absolutely terrible.
Like security cookies instead of canaries,
Yeah, exactly. All right. So let's go through this a little bit. Okay, I don't want to turn this into an intro to assembly or anything like that, but I'll hit some of the key points, if you will. All right. So one thing that's always interesting is when I see an instruction like this, I just rep stas double word pointer, and then we see RDI. RDI is apparently going to be where all of this is going to be stored. All right. So the rep says repeat. So repeat by how many times? How many times are we going to repeat this? Well, that is going to be stored inside of ECX. So if you're looking at things that might be a loop of sorts, like a do while loop, for loop, or a while loop, or whatever, a lot of times they're going to have some kind of condition that says when they're going to be done looping, some kind of index that says, hey, you're done. There's no more iterations to do. So that can be stored inside the ECX register, and you see 24H, H being hex. So hex 24 times, this is going to go ahead and be repeated. Okay. Excuse me. And one of the things that you can do inside of WinDbg is use a command called .formats and say, I have no idea what 24H is. Can you help me out? And I'll show you all the different formats for that particular value, even a time date stamp, going back to apparently 1969.
Epoch.
Yeah, so kind of cool, right? To go ahead and play around with different formats. All right, we'll use that a little bit later when we actually debug this and let it run. So we see another rep command. Okay, so automatically when you see rep or repeat, automatically look for a few things like the RCX register for a count, and look for the destination where it's going, and also a possible source because it's got to be pulling it from somewhere. Okay, call instructions. Kind of like what I was talking before about optimizations and efficiencies, if you will. Being inline will not have a call instruction. Okay, so going down a little bit further here, let's see what else is cool to take a look at. Let me move this over just a little bit more. Okay, so we see a call to heap alloc. All right, so dynamic allocator chunk of memory, get last error to say, hey, did it fail? Why did it fail? And we can go ahead and printf the error message. And then if we're good, we go ahead and move along, printfing the status as we go. Right, printf debugging is kind of cool, but it's always up for debate, right? If printf debugging is actually legit or not. But yeah, so nothing too crazy here. One of the things that you can do is, obviously, because we have symbols, we can take a look at certain things and take advantage of some things. Like this will go ahead and tells us that intrinsic XOR bang and then string, this is going to be shoved in RCX. And it's like, well, what is this string? So we can check out a few ways to do this. There's a D command for like displaying types or dumping types. So DC will go ahead and take an address and dump the addresses and the hex and the ASCII or Unicode representation of the bytes over here. Okay, so let's see if we can find a different one other than just a format strings. That's just percent O2X, which is boring. Let's see what this one says. All right, so that one's just, after. Okay, so we're saying after. There's also the DA. All right, so dump ASCII. I'll go ahead and say, I know how to find this ASCII string because I'm looking for a null terminating character. And so I'll go ahead and say, this is the entire string that's going to be sent out to the terminal or whatever for the printf function. Okay, so that's kind of like a high level summary of moving around and playing around with just a couple of WinDbg commands. And one of the things that we kind of want to take a look at, and that's the whole point of the stream, is the intrinsic functions. Okay, so I intentionally made the wrapper function for the XOR routine so I can show you kind of what the call looks like to get into the wrapper function. And if you don't know the full name of it, you can just type in XOR with the wildcards around it, and it found it for us. So you can go ahead and just click on that. Okay, cool, thanks. And we have the address for that. So I can take that to the disassembly window, paste that in there, and we're in the same spot, okay? A lot of times I prefer to be over in the disassembly window just because I like the color coding, if you will, for the instructions and some of the offsets and the values. In the command side, you don't really have that. So, it's whatever. So up to you where you like to spend some of your time when you're looking at some of these instructions. Okay, let me move this over again. Inside of this one, the intrinsic XOR, we know we were passing in a couple of parameters, 3 of them to be precise. The first one is going to be an RCX. The second one is RDX, and the last one is going to be an R8. If there was another one, it'd be an R9. And anything additional after that would be on the stack. Okay, so those are being saved off on the stack, and a little space that's reserved for these functions to kind of, I call it like a scratch space, if you will. So the called function can do what it wants there with that little space. But what it's doing here is it's just saving those first 3 parameters. We have what's called this is the part of the whole function prologue. And then this sub RSP, basically we are creating what's called the stack frame to say, hey, this is how much space I need on the stack for this thread for my function. And let's see what 1E8 is. Oh, come on, hover. There you go. So the decimal signed value is 488. You could also just pass that to dot formats. I know that little tooltip was pretty hard to read there. Okay, so dot formats, there you go. All right, now we see another rep. All right, another rep instruction. That's going to repeat ECX times. I've already shown you that one. I've shown you that one a couple of times now. Okay, and then what we're looking for here in all these move operations, this is going to be how our XOR key is being set up the first time in its local variable. Okay, each byte at a time inside the array. All right, our little key array, and we can see all the indexes and stuff like that. So this is kind of what that looks like at the disassembly level. And then here, this is where we actually get to see some of the intrinsic functions. Okay, again, what's great about these intrinsic functions is they're highly efficient. We have a single instruction that's going to basically take our key and load it up, right? Load it up in an XMM register, one fell swoop, or 16 bytes at a time, if you will. Okay, so cool. So we got that. And we're just paying attention here to XMM registers. Okay, so some of the other ones we see here, we're going to go ahead and start to prepare the M128 variable to go ahead and hold to hold that key after it's already been loaded up, we can go ahead and start to process it. And then we see the XOR, okay, the XOR PS. Okay, so we're good to go there. And then once that's all said and done, eventually below that, I'm scrolling way too fast. It skipped on me. Okay, so after the XOR is done and you're handling 16 bytes at a time, eventually you're going to have to move around and handle some of the leftovers. And that's what this XOR instruction is probably doing for us. Okay, so you can take a look at that and spend some time there to figure out exactly how that's doing it. But typically, this is kind of what you'll see inside of a for loop that will do an XOR operation against those remaining bytes that didn't evenly fit into a 16-byte chunk. All right, call them the leftovers, the scraps. All right, so that's enough. A little walkthrough of this one. So let's go ahead and just debug this. We'll hit stop debugging, even though we never were in the first place. We opened that up as a dump file. So let's go ahead and kick this off. Launch executable. Okay, cool. So now we are actually in memory. We have some DLLs that have been loaded. N2 DLL will always be there. That's the system loader. So you can count on that one to be there. Kernel 32, kernel base, optionally could be present. And VC runtime, of course, because we linked with C runtime, so on and so forth. Okay. Now what we can do is we can set up breakpoints. Now that we're actually inside of a an executable image that's there, it has a thread that's running. We can set up breakpoints on certain functions of interest. So we could set up a breakpoint on the main function if we wanted to. But what I would like to do is basically just jump straight to the XOR wrapper function so we can start stepping through some of that stuff and then take a look at those specific registers. And I'll show you how to look at those specifically at the command window here. All right, so let's see if I have... There we go. So just bring that up again. I just want to copy and paste this and set up a breakpoint there. So BP sets up the breakpoint. BL does a listing of all the breakpoints that it sees right now. You can disable this, which means it'll still be present, but the breakpoint won't be hit. And then clear. Clear is to go ahead and just get rid of this thing. All right. G, we'll go ahead and let this thing go. And because we have our symbols and it knows where the source code file is and all that stuff, it went ahead and opened up another window, which a lot of times personally I find to be very annoying. But as you're getting started with some of this stuff, it could be very helpful to see where you are inside of the source code at the same time when you're stepping through some of these assembly instructions. Okay. Let's see, looking at the questions here.
Most of them have been
Already
answering.
answered? Okay.
Yeah.
All right, cool.
There might have been one.
Yeah, the SIMD, yeah, single instruction, multiple data, which is how we get that efficiency. All right, yep, cool. So inside of the source code file, main.c, you can see where the breakpoint kind of is. Let's go ahead and just try to X that out for now. It's probably going to come back and haunt me for a while. Okay, so going down here, what you can do is a couple of things. You can go ahead and say, hey, when we step instructions, you can do so at the assembly level, or we can step through one line of source code at a time, which one line of source code is probably going to be quite a few assembly instructions, okay? Which, it, depending on what you're trying to do, it could be exactly what you want. All right, so let's see. Some of the GUI related functions over here are buttons. Step out, basically say, go ahead and finish this function. I want to get out of here. I don't like it inside this function. Help me. I'm stuck. Step into. So if there's a function that's about to be called, you don't want to step over the call and skip it. You want to step into it because there's something of interest that you want to see, and step over. Step over to go ahead and go down to the next instruction, or to go ahead and go down to the next line of source code.
Someone asked on Discord, how is the trap flag used in correlation with the steps, stepping and stepping in, stepping out?
Specific to stepping in and out?
I think just in general, like when you're using debugger to step instructions or return, continue to return and stuff like that, how the trap flag operates.
Oh, I mean, I guess you could try to watch that inside of e-flags or whatever, if you're familiar with e-flags or extended flags. All these different placeholders or bits, like bit fields that make up the e-flags. So as you do a step, you could try to pay attention to some of that stuff if you'd like. But like trace to return or run to next return or run to next call, stuff like that is somewhat self-explanatory, I'd say. Go ahead and execute all the instructions until you come across a crawl. Go ahead and run until you find your first return. I know a lot of times debuggers will go ahead and actually modify the instruction that you'll go ahead and insert like a CC, a little interrupt, because we're debugging it, and it'll make modifications. The modification isn't really shown to you because this is actually lying, right? It's kind of lying to you, if you will. It's not going to show you that modification of that byte, like this one up here, all these CCs, all these int threes, those are interrupts. And I like to call those, I like to call this space, like in between functions, as a code cave or slack space or whatever. You can store data there. You can store shellcode in there. But yeah, that's a different, completely different stream.
Yeah, I did a stream once on a mitigation called export address table filtering, and it talks about how guard pages are set. And we do get into the trap flag on that one. So if you go check out that video, you'll learn more about how the trap flag works and gets set.
Oh, cool. You got a whole stream about that. Nice.
Not about the trap flag, but just
No, okay. I was like, man,
that would be a boring
detailed. A whole hour about the trap flag. Way to go, Steve. But yeah, so cool. Good question. All right. So we got the breakpoint hit. And what we kind of want to do is look to see how everything is coming around. And I want to look for this one here, the very first instruction that lets us mess around with an XMM register. So that's that address. Let's go ahead and set a breakpoint on that address. And we'll just go ahead and let it go until we hit it. Okay, cool. And it says here inside of a source code that came back to haunt me, this is the load you instruction, right? We're not going to load me, we're going to load you. So we're going to go ahead and load that up inside the XMM register. Okay. And I have a little comment here for anybody who is looking at it. The specific WinDbg command that you can use to go ahead and take a look at the data that is inside of the XMM registers. WinDbg by default won't show you these registers. Okay, you can make modifications over here inside of the registers window to do that. If you want to see those, you can. But you might as well just stay in the command window and go ahead and try to look at some of the stuff manually. And you can also have more control about how the data that is stored inside of that register is to be presented or displayed inside the command window here. All right, so let's go ahead and let that go. Or we're not going to let it go. We're going to step over. Okay, so we step over. And I made a little oopsie. I still had it on stepping over source instead of assembly, which whatever, that's fine. Not a big deal. All right, so the next piece you can see on the source code, we're getting ready to hit the for loop. We're going to go ahead and grab 16 bytes at a time to XOR this stuff. But let me get rid of that so I have a little bit more space. And let's go ahead and let's run or execute that R command, right? R is a way to display registers. So R by itself will go ahead and dump the registers. All right, and it's an exact display over here of what you see in a registers window. But by default, it's not really showing us everything. You do RX to show the XMM registers specifically. And this is our XMM0. This is what we just used for that first intrinsic function. And this data is nonsense. Okay, that is like ridiculous. I don't know why by default it's showing us this in that way, but it's no good to me. I don't like it. So what you can do is I'm just going to copy and paste the command from the source. I'm lazy. Copy paste so many things in my debug life. All right, so we go ahead and say, I want you to go ahead and show me the 16 bytes. All right, remember, inside these registers, we're dealing with up to 16 bytes at a time. That's how we get some of that efficiency there. So we'll show me 16 bytes UB, right, unsigned bytes. And we get this hex stream, if you will, call it a hex stream, of bytes, starting with 0D, FC, EB, blah, 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 all the way to 1F, which is our XOR key. So we can go back to source code just to verify. And yeah, we see our XOR key starting at 1F. And then you'll notice that notice endianness. All right, it's not going to be the straight representation of what you see inside of our source code, right? Always remember your endianness. All right, little endian, big endian, host order versus network order, right? So keep that in mind as you go through some of that stuff. All right, so now we actually verified that our XOR key has been loaded into the XM register. So now we can go ahead and start that for loop and actually XOR all that plain text data with our key 16 bytes at a time. Okay, so we can go through here. Let's come down to the XOR instruction, the XOR intrinsic instruction. I'll set a breakpoint there and we'll go. Okay, sweet. And since the source code is here, I guess I'll talk about it. All right, show you the C side. MMXOR 128, the current chunk. All right, remember, this is the current chunk against the loaded key. And we'll store that off in its own little local variable called XOR. All right, cool. Goodbye. And now let's go ahead and step that. Okay. And now XOR, the XMM register has been updated. So let's go ahead and take a look at the update. And there we go. We have a new value here, 70 DC 9F, blah, 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 and then 4B. Okay, it's going to start here, right? 4B 43, 55, right? That's what it would be in the end if you were to try to like printf this current chunk that's been XORed. Okay, so the first round is basically complete. We have the first 16-byte chunk of the plain text string that has been XORed, so sweet. Then this is go ahead and loop over as many times as it needs to go ahead and grab 16-byte chunks at a time. Okay, and then let's see here, going through towards the very, very end when we have the stragglers. Okay, I'm just going to look at the first XOR routine. And this is what you typically will see if you're doing a traditional XOR operation from the C side, trying to create like 4-byte hash or whatever. So this is that signature, if you will, that some EDR products, I guess, could look for to say, hey, it looks like you could be trying to obfuscate some data. All right, so breakpoint is set up. And the source code file came back, and we are indeed at that spot where we're going to handle all the leftovers, all the scrabbles. Okay, so that's what's going to happen there. And this one, instead of happening, obviously, this one's not going to happen at 16-byte chunks at a time. This is going to handle every single remaining byte individually. Okay. All right, sweet. So as that goes through the motions, I'll go ahead and XOR the scraps. And when everything is all said and done, typically when a function is about to finish, if it has a return value or a return type, that'll be shoved into the RAX or the EAX register, unless you're passing in like a pointer to that data and we're storing that data through a pointer, right? But typically, RAX is saved for the return value. All right, so we could go ahead and let this thing go ahead and completely finish out because we already took a look at those intrinsic functions that basically give us our XOR routine. And we'll just go ahead and hit G, and let me get rid of that. Okay, there we go. We're done. The syscall is invoked to go and terminate the process. Sweet. Let's see what it printed out. 4B4355 ending in 4E. That's exactly what we saw before. So awesome, right? Nothing too crazy. Okay. Yeah, big racks. Yep, good old big racks. Yeah, so that's basically a crash course into compiler intrinsics, compiling down that source code, looking at said source code inside of WinDbg, and looking at the XMM registers and seeing how they get loaded up with those intrinsic functions, and how to look at those with the register command inside of WinDbg. Right now, where can we go from here? So we saw some basic operations, cool. We saw a custom XOR routine, cool. But what next? All right, so let's talk about what you could do next. Okay, so let me open up a different project here. Okay, I know I'm switching to C++ for just a second. All right, this isn't not going to do an intro to C++. There's a whole separate stream workshop series that I'm going to do for that. But this is what you could do with an XOR routine or whatever. You can create an intrinsic hasher with a Unicode string data type. Internally, Windows loves to store strings inside the structure as a Unicode string. We have a couple members in there, length, max length, and the buffer, which is the goods. That's actually where the string is located. But we can take what we just learned about some of those compiler intrinsics, apply that same kind of concept. We're just changing the data type. The data type of what we're XORing, instead of it just being a traditional char array, like this is a test string or whatever, we'll go ahead and say we're going to mess around with a Unicode string. Okay, so we can go ahead and account for that. We have to modify things just a little bit. And honestly, this function right here isn't too specific to C++. We still have the intrinsic functions. This set 0 does exactly that. It's a way to nullify or zero out and initialize M128 typed variable. And then we see here, we'll go ahead and make our little loop-de-loop, calling the XOR, or invoking the XOR intrinsic function against our chunks. Okay, so the XMM registers, they can work again on 4-byte, 8-byte, 16-byte chunks as you need to. It all depends on what the data type is that you're messing around with and what you're trying to load up inside of the XMM register. Okay, so in a nutshell, what I was doing here is just making some hashes of some DLLs like kernel base, kernel 32, NTDLL. So nothing too crazy, and run it through that, because what you could do with this, if you wanted to, is you could take this code here, like you could take this entire intrinsic hasher function and use this to help create like a pick binary, position independent code, to use this inside of your shell code to go ahead and walk the process environment block, looking at the hashes of DLLs that could be of interest to you, like kernel base. Kernel base could be of interest because you're looking at the export address table, looking for a function that you want to call dynamically through it. So we want to create hashes of module names and create hashes of function names. All right. So this is where you could take things based on what I just showed you. Okay. So that's one example. Another example, going into more C++ type stuff just briefly. If you wanted to actually align your array that you're using for your XOR key, you can use the align as keyword and say, hey, I want this to be on 16-byte alignment. And you go ahead and just say, all right, cool. Let's go ahead and create our XOR key. And the only thing changing here for this, you see the same kind of thing, load U, XOR, and then store. All right, load, XOR, store. That's basically the three primary things for this XOR routine. Hey, the only thing changes for this piece, though, is instead of dealing with a chart array, instead of dealing with a Unicode string, we're dealing with a byte vector. Okay, that's it. Byte vector is basically the same thing as an array, all right? Just a C++ data type. Okay, so that's where you could go. Maybe a little bit later, like Steve said, if I come back later this year, we could dive deeper into C++ intrinsics, creating like a crypto function, do some AES encryption using intrinsics, compile it down to shell code, and execute that shell code just as a small POC to show that it can be done.
You mean when you come back later this quarter?
This quarter. Yeah, yep, there you go. Yeah, we'll see. But yeah, so that's pretty much all I wanted to cover. Does anybody have any questions about anything? I think I gave most of the resources.
Someone asked if we can break on syscalls and WinDbg.
Not from user mode. Oh, well, yes. You just say BP on the address. But if you want to follow it into the kernel, how I was doing the setup, no.
Yep.
You'll miss all of that. So you got to do some kernel debugging to go ahead and get into that.
Yeah, you'll
but
see
yeah,
an instruction like sysenter, and yeah, it's like snap your fingers and you're already back out of the kernel.
yeah, yep. So anywhere inside of NTDLL, where all the syscall stubs are located, you can set breakpoints anywhere you would like inside of NTDLL, and yeah, it'll hit, it'll break. But I assume what you're wanting to see is that transition to the kernel. You won't see that. It'll be blind. You'll be blind to that unless you're doing kernel debugging.
You know, it'd be a great stream. I think would be easy for you to do as well if you wanted to do it. Would be people a lot of times are asking around context switching when you're in kernel mode. So obviously, like if you're debugging a Ring 3 application like a Chrome tab and you're using a kernel debugger, obviously there's so much going on. Like how do you get specifically into that context state? Because oftentimes you think you're there, you feel like you're there, but you're actually not there, and things change. So
yeah, absolutely. Because when you're kernel debugging, it's great for seeing all things in the kernel. But if you want to see something specific happening in a user mode process, it's cool to have that kernel context, but you got to sometimes get into that context of a user mode process. So you kind of break into that context and get out, and you're done. Any high level tips for debugging large programs with lots of imports? It's a pretty vague question, I think. I'd say a high level tip for debugging a very large program, I would say have kind of a goal of what you're trying to see, of what you're trying to debug, unless you're just trying to figure out exactly what it's doing. Every single instruction, like if we're trying to, let's say, on the side, I've been doing some research right now on reverse engineering a EDR's kernel component, like a file system mini filter. Right, those are pretty large programs with tons of imports. A lot of things happening with those EDR components. So what I do though with that large of a program is I have a very specific objective that I'm trying to do, instead of just basically debugging the entire program. Right, I don't have time for all that. I want to take a very specific approach and look for something specific.
Yeah, there's an old header file out there. It's hard to find nowadays, but it's called band.h, and band.h was part of Microsoft's SDL process, the security development lifecycle, where it was a massive list, not massive, but a list of deprecated or antiquated functions that are dangerous. And there were two versions of it. There's a simple and an advanced version. And like, that's a good start, where we actually in 760, we have you write a little script, and I posted it online before, where you run this IDA script against your input file, and it simply goes to the imports table or your procedure linkage table and global offset table in Linux, and it looks for any of the banned, antiquated, dangerous functions, and it sets breakpoints on them and lists them out. So like, that's one good way to approach the imports when you're looking for bad functions.
Yeah, specifically for that vulnerability research. Inside of WinDbg specifically, I guess you could do use the X command with some wildcard searches to look for imports of interest, like a str copy, mem copy, that type of stuff that could be vulnerable, for sure. Intrinsics are good for AV evasion. Yeah, definitely. So I've bypassed several products. And when I say bypass, I'm not just popping calc. Actually getting my stage from my C2 infrastructure to go ahead and get that. So yes, absolutely. It can help, again, dependent on the EDR that you're going up against. What was the other WinDbg package I posted? No, Steve, is that for you? I think that one's for you. Debugging the hypervisor.
Which question?
AZ. What was the other WinDbg package you posted on X? A live demo stream of debugging.
Oh, yeah. There's two. If you go to the Off by One YouTube channel, look at the live page, and it shows all the past videos. There was two that we did on hypervisor debugging. One was with JTAG debugging, and the other one was through a different method. Those you can go check out.
Cool. I think we're caught up with any questions.
Did you answer the question around
else?
Sec 770?
Oh man, yes. I like to say yes. Steve, I deflect that to you. When can I write 770?
I think John's going to be working on a advanced red team course first, but yeah.
Yep.
The challenge comes in with these courses is a lot of them are very niche. So for an author to take the time to go and write multiple days of content and then to run it, if only a few students show up, obviously it's not worth it for the author side. So that's one of the reasons I started this channel, is to like do this kind of stuff without having courses. But that'd probably be something better for like a one-off black hat training or something. But it's possible if we get enough interest.
Yep. Yeah. If y'all bug Steve enough, generate some of that demand. What I have in store for that course is it's going to be a quick ramp up to get into the kernel. Do some kernel dev specifically for like red teaming dev, that type of stuff. Want to take it deep all the way into looking at packets, net buffers and net buffer lists, how to manipulate packets, hide your traffic, your C2 traffic, mask it a little bit, if you will. How to do a lot of that stuff straight from the kernel, and diving into file system mini filters for red teamers, stuff like that. So, and also trying to take advantage of EDR mini filters as well. So that could be some cool 770 stuff. But yeah. Besides intrinsics, are current cool tricks to bypass AV. There's always cool stuff coming out all the time. Yeah, quite a few. There probably could be a stream on some of those. So maybe somebody could do
Do
that
you,
someday.
do you feel like bring your own vulnerable device driver is still useful, or is that starting to die down?
It depends on the organization.
Yeah.
I would say, depending on the org, yes, it can be highly useful and still very relevant. But as things get more secure, as EDR products get smarter, they're moving more into the kernel. They're looking for some of that stuff. So maybe it's not going to work for you in that particular environment. So it's always this back and forth motion. Yeah, cat and mouse. Always a cat and mouse game. So you just got to be aware of your environment that you're getting into. Yeah. Cool. I would say if anybody else has any questions, feel free to hit me up on Discord.
Did you see that one around asking about asset intertext source point debugger package? I haven't used it. Have you?
No, I have not.
Cool.
Yeah.
All right. Well, I really appreciate it, Jonathan. It's really, great of you to come on again. I know I joke, but yes, I will keep bugging you to come on and talk about debugging. That's why it's debugging, right? Get it? Bad joke. But for everyone else, have a great weekend. I'm hoping to identify some good streams coming up. It's always, a bit of a challenge to find folks who want to donate their time to come on here and do it. And we've been really fortunate that so many people have. And I've got some things I want to share as well. So we'll start announcing those very soon. But otherwise, have a great weekend, and we will see you next time. Thanks, Jonathan.
Yep.